In our last video, we talked about how replication is template driven, primer driven, and semi-conservative. And in particular, we stressed the importance of how we build off the 3' end. And the whole idea of a primer is that we are building off of RNA and we are going to then build DNA. Now keep in mind, we've got some problems here. First of all, we don't want RNA in our new DNA molecule, and we're going to have to get rid of that. The other thing is we're replicating this side and this side, but we're not replicating up here, and we're not replicating down here. Both of those problems are going to have to be solved, but not now. What I'd like to do at this point is take a moment and focus in on this area right here. We have a template, which we're going to use to copy. We have a primer, which is the 3' end of RNA, and we have a new DNA strand that's going to extend. We're going to zoom in on that down at the bottom of the page. So let's move that out of the way and go down here. And like I said, this is a zoom in on that area that we circled above. Let's go ahead and label this out very carefully. Let's say this is our RNA primer, and this is where DNA has just started to be synthesized. So that green border is where we've taken the RNA and started to make DNA. In fact, we've already added a couple of nucleotides of DNA. So this is the primer. This is new DNA, and this down here is the old DNA, or what we call the template of DNA, the stuff we're going to use to copy. Here's a couple of things I'd like us to practice. Let's pause and answer a whole bunch of questions. First of all, I'd like you to take this sugar right here, and I'd like you to label all of the numbers of the carbons on that sugar. So let's number those. Next, I would like to say, what if we had an A right here, an A right here, and C right here? What would be the identity of the bases that I'm going to show? What would be the identity of these 3 bases? Let's try that. Take a moment, pause, and see if you can come up with everything. Okay, let's start with the base pairs. First of all, let's start with this A right here. If we have an A here, and we had previously added in a base that's coming off the backbone here with new DNA, then what we would expect is this would be a T, because A and T are always going to be present. In fact, that's what we are going to call template driven. The T is brought in and added to the A, and presumably that happened in some previous instance. Over here, the C means we're going to have a G. Now, this is, by the way, a nucleotide that is new. In fact, let's call that a new nucleotide that's going to be added to this growing DNA strand. And we'll talk more about that. That's the key part here. Lastly, I want to go back to this base back here, where we have an A and an RNA up here. We haven't said it yet, but RNA does not contain T's. They contain U's instead. And when we have an A and we're going to bring in RNA, we use a U. So an AU is going to be a base pair that we see in RNA, and an AT is going to be what we see in DNA. All right, let's go ahead and label out the numbers on this base right here. This is critical as we consider this last terminal ribose there. What we can see is that we have a 1' right there. I'll leave the primes off just to keep this neat. But we know that's 1 because the base is attached to it. This is 2. That's deoxy. That reminds us that it's DNA. There's 3, 4, and the exocyclic carbon is 5. So what we have here, I'll put a prime on that one. We have a free 3' OH. That means this is the 3' hydroxyl. Okay, at this point, we're ready to take the DNA terminus, 3' hydroxyl, bring in a new nucleotide that we're going to use to extend. And there's 3 parts that are going to happen to this. First of all, let's make a note. We use what are called D, that's a little d, capital NTP. We use DNTPs. That is, we use 2' deoxy, nucleoside, 5' triphosphates. You must have it be 2' deoxy, and there must be 3 phosphates attached. Second of all, we're going to have the 3' hydroxyl attack what we call the alpha phosphorus, or I'll just call it the first phosphorus atom, the first one coming out in the nucleotide. Let's put a pair of electrons on there. We're going to have this attack from that oxygen to that phosphorus, and we are going to break that bond right there. We're also going to break this bond that happens next. And that's what I want to say. Third, we are going to make a 1 phosphodiester bond, a 3', 5' phosphodiester bond, and we're going to break 2 phosphoanhydrides. I believe we talked about phosphoanhydrides in a previous video. If we didn't, let me just remind you that when you have 2 phosphates together with each other, these are phosphoanhydrides. We'll just call those PA. And what we end up doing is connecting this carbon-oxygen here to this P double bond O. That's a phosphoester. There's already a CO P double bond O there. We end up creating that phosphodiester backbone that we talked about. The reason, by the way, that we break 2 phosphoanhydrides is this process drives the reaction with energy release. That's going to be something we move on into in the future here, in the next chapter, the next unit. But for now, let's just say making that phosphodiester bond is critical because that builds the backbone, and breaking the 2 phosphoanhydrides releases energy and allows this process to be favorable as we move forward. At that point, we end up with a new bond that connects the new backbone. And notice that we end up with a new 3' hydroxyl ready to go and attack the next nucleotide triphosphate that comes in. This is a process that repeats itself over and over again, and the upshot is that we end up moving and replicating in this direction, adding on to the 3' hydroxyl as we said. Okay, very important video here. This is how we make the critical backbone bond, and it's a little bit mechanistic, but hopefully this is something that you'll understand.